I want to talk to you about another new concept. Before I'm writing down the name of the topic today, I want you to take a look at this curve. So I have the coordinate system, y, x, okay, and on this system I draw a curve, and then the curve will look like this, okay. And I draw a line y equal x. The line y equal x, that I make the angle with x-axis at 45 degrees. So this is the line y equal x. Okay. Then I draw another curve. Okay. I use the red color, or maybe I use the let's use this one, purple color. I draw another curve that kind of symmetric to the first curve, okay, about the line y equal x. That's what I'm gonna do. But before I'm doing that, I want to ask you this. The curve over here, do you think that this curve represents a function? Well, if you apply vertical line test, right, this curve over here represents function, because vertical line test cut this curve at only one point, the vertical line. So this curve represents a function. So I call this function function f, for example. Okay, it's fx. Okay. Now I'm about to draw another curve that's symmetric about the line y equal x to this curve. Okay, so I kind of mirror the curve fx about the line y equal x. So if I mirror them, so it's going to give you something like this, right? Kind of like that. Okay. So this point here, I mirror them. You have another point here. This point here, I mirror them over the line y equal x. I have another point over here. Okay. And do you think that the curve I just mirror from fx is represent function? Yeah, it is, right? Because if I apply vertical line test, it gives you it really represents a function because it passed vertical line test at one point. So because it represents function, I name it. I call this curve g of x. Okay. All right. So this function g of x here, okay, is the second version, is the version of function fx after you mirror fx about the line y equal x. Okay. The function g of x here, in mathematics, we call the inverse function of f of x. So today we want to talk about the topic will be the inverse function. Okay, inverse function. Okay, inverse function. Alright. So again, I say gx is the inverse function. Gx is inverse function of f of x, because g of x is the image of f of x over the line y equal x. You mirror them, right? And because g of x is the inverse function of f of x, I can write g of x as, so I can say fx has an inverse function. Okay. Okay. Fx has an inverse function, and that inverse function is g of x, or we can notate the g of x as g of x equal to f of -1 of x. Okay. So f of -1 of x denote the inverse function of x. Okay, f of -1 of x denote inverse function of f of x. Okay, inverse function of x. So what we know about the inverse function? What do we know about the inverse function? We know that if x considered as the input of f of x, then x is also considered as the output of the inverse of the inverse of f of x. Okay. What I mean over here is that if f of 1 equal 2, so 1 is the input of f of x, right? 2 is the output of f of x. Then f of -2 of f of -1 of 2 inverse of f at 2 equal 1. Okay, so right now the output of the original function become the input of the inverse function, and the input of the original function become the output of the inverse function. The formula that if y equal to fx, we already know this. This is the notation for the function. Then f to the -y of y equal to x. Okay. So you have to memorize this. Any questions? Okay. So I'm gonna put over here as the definition. Okay. Okay. Let me give you another example. How about this? Example. Let me see. Let me see. I can draw a beautiful graph, and but the thing is very hard for, because this is, you know, this whiteboard over here is very hard for me to graph a beautiful one. So let's see. Okay, I can do something like this. I have the graph like this. Okay, and I have a linear line. It's a line. So I have the line y equal x at 45 degrees. Okay. And sorry guys. Then I have a line that is look like this. something like this. For example, 1, 2, 3. Okay, so I have a line that's something like this. That going through. They have the slope is 3, and the y-intercept is also 3. So we have the first line. We have the line that look like this. So this is 3 here. There you go. So this is -1. Okay. So I have the line like that. Okay. Now I'm gonna mirror this line over the line y equal x. Okay. So I mirror them. So they become what? So this become this one, right? And this one become this one. So I have another line kind of going through like this. So the first line is y equal to 3x plus 3. Okay, 3x plus 3. Now I'm going to mirror that line through the line y equal x. Okay, so I'm going to have this line. Okay, so this mirror over here, so I'm going to have something like that. Okay, it's not really perfect. Something like that. So it's very hard to grab the symmetric one. So this over here is over here, right? Then it's gonna cut here. So it's kind of something like that, you know? There you go. Kind of something like that. Okay. So I say the function g of x here is the inverse function of f of x here, because it's symmetric about the line y equal x. Okay. Let's consider as the example of the inverse function. Okay. But the thing is that by graphing, sometimes some of the function is very hard for you to know if it has inverse or not. Well, you can graph it like this manually, you know. But the thing is that sometimes you graph it, and the one after you graph does not satisfy the vertical line test. Then it means that that function doesn't have inverse. Okay. Then the mathematician find out another way to check if the function has the inverse or not. Okay. They use something called a vertical line test. Okay. I'm not vertical line test. Something called horizontal line test. Okay. And the horizontal line test say that if you put a horizontal line on the graph of any named function, and if it cut the graph at one point, then it has inverse. If it cut at 2 points, more than 1 point, then it doesn't have inverse. So you see that if you apply horizontal line test here, it cut the graph at 1 point, so they have inverse. If you apply horizontal line test here, it cut at 1 point, it had inverse. Okay. So I'm gonna put over here remark. We can check if the function has inverse by applying horizontal line test, okay, apply horizontal line test, which is, okay, if horizontal line, okay, let me erase this. Horizontal line cut the graph of any function. If horizontal line cut the graph of any function at more than one point, okay, then that function does not have inverse. Okay. So you see that the line over here has inverse, right? Because you apply the vertical horizontal line test, it cut at one point. Okay. Or I can give you something like this. Example. If I have a graph that looks like this, and I have something like that. I have something like this. Okay. I know that you see that if I apply the horizontal line here, it cut at it only one point. If I apply a bunch of horizontal line tests, it cut only one point. So I know that this function fx here has an inverse. It has an inverse. And we can get the graph of the inverse by drawing the line y equal x, and you mirror that about that line. Then you do the same as the example. Okay. So that is the way to check if the function has inverse or not. Okay. By looking at by applying the horizontal line test. But in order to apply the horizontal line test, you have to graph that function. Okay. Another condition to make to guarantee one, it's not guaranteed. It's another condition to satisfy that that function has the inverse. It is the function must be one-to-one function. Okay. So on the second part, I want to talk about one-to-one function. Okay. What I mean over here is that a function has an inverse. Then, first of all, it must be one-to-one function. It must be one-to-one function. If it's not one-to-one function, we know right away that that function doesn't have inverse. Okay? I didn't say that for the function to have inverse, it must be it satisfies only the case one-to-one function. Okay? Because it's not. Okay? But one of the conditions it must satisfy is one-to-one function. Okay? That it must satisfy another condition, but I don't want to mention it over here because in order for a function to have inverse, it must be a bijection. Okay, but I don't want to talk about that terminology because it's for another level. But one of the conditions for a function to have inverse, it is to be one-to-one function. It must be one-to-one function. But what is one-to-one function? A one-to-one function is a function that satisfies that if x1 different from x2, okay, then fx1 must be different from fx2. Okay, that is condition for a function to be one-to-one. Okay, if x1 is different from x2 and fx1 the same as fx2, then it's not one-to-one function, and then because it's not a one-to-one function, then the function is doesn't have inverse. Okay, that makes sense to you? Okay, so remember that. Remember that. For example, I have something like this. I have a graph. Okay, I have something like this. Okay. I have x1 over here, and I also have x2 over here. So you see that x1 give you fx1. x1 is different from x2, but the thing that the output is give you the same thing as fx right here. I call that fx3, for example. Okay, so you see this one doesn't have inverse function. Okay, because x1 different from x2, but x1 also give you fx3, and x2 is also give you fx3. This give you the same thing. So that's why this function here doesn't have inverse. By applying vertical line test, horizontal line test, we see right away that. You see that if I put the horizontal line over here, it cut at like 3 points. Okay, cut at 3 points, and then it doesn't have inverse. Okay, so there's no inverse. There's no inverse. I can give you another example of a one-to-one function. Let me see. Example 2. I have fx that contain 3 points. 1, 4. Okay. 2, 3. Okay. And 2, -2, 4. Okay. We want to see, question, fx is 1-to-1. Answer. Okay. We see that this function is 1-to-1 function or not. So you see that input over here is 1, different from the input here -2, but the output is the same. So it does not satisfy this. So you see that x1 is the same, is different from x2. Okay, okay. x1 is 1. It's different from x2, which is -2. Okay, if x1 different from x2, in order for a function to be 1-to-1, fx1 must be different from fx2. But the thing over here, fx1 is 4. It's the same as fx2. fx2, which is f of -2, f of 1, f of -2, is also 4. So you see that it does not satisfy the condition, and therefore fx is not 1-to-1. And because it's not 1-to-1 function, so fx does not have inverse. Okay, fx does not have inverse. Okay. Okay. So I want you to take a look at the first graph I draw. You see that in order to get the inverse of the function, you just need to graph it over the line y equals x. Okay. Then after you graph and you check the vertical line test, if the image of that graph satisfies vertical line test, then the function, then it means the original function has inverse. But the thing that sometimes it's very hard for you to graph to check a function that has inverse of each other. Then what you have to do is you have to check it algebraically. What I mean over here, if I give you two functions and you want to see two functions that are inverse of each other, okay, you have to compose them to each other. You remember back in the day we learned how to compose two functions f and g. Okay. After you compose two functions f to g and you compose function g to f, and you see if it turned out to be the same as x, then we know that the function, those two functions are inverse of each other. Instead of go ahead and graph it and see if it satisfies the vertical line test or horizontal line test or not. Okay, so that is the algebraic way. So on the third part, I want to talk about two functions are inverse of each other.